Hello students. Okay. Uh, as in the previous class we have done a problem on bar element, stepped bar element. In the previous session we had solved on problem number 2 and problem number 3. Uh, Problem number 2 was simple stepped bar, and problem number 3 was 3 stepped bar. Problem 2 was 2. Okay. Uh, I hope you all have completed it and you will be submitting the assignment by today. Okay. Coming to the next problem, problem number 4. This problem, how is it different? In this problem we will be analyzing a tapered bar. Okay, the bar what we have taken in this here is tapered bar, that is varying cross section. Okay, how the varying cross section bars are solved manually. Okay, so the given figure you can see one side the height of it is around 60 mm and the other side it is 30 mm. Okay, and the thickness of this plate is 5 mm and thickness of plate is 5 mm. Okay, this is nothing but it is cross sectional view of it. Okay, now I also see that the load is applied here at the center. Load is applied here at the center. Okay, now let's read the question. What's the question? Question is, determine the nodal displacement, stress, strain in each element and reactions at the fixed end for the thin plate of uniform cross section 5 mm as shown in the figure. Take Young's modulus as 200 GPa and model the plate with two elements. Okay, and model the plate with two elements or with the two bar elements. Okay, how to model this? If you see the stiffness equation K, K is A1 E1 by L1. There the A is not varying. It is a constant area throughout its section, throughout its length of the element. The area is constant. Okay. Now here the area is varying. Now how to do this? Now what we'll do is, instead of taking it as a tapered bar, we'll analyze it as it average area of it is considered. That is, if I just take it equal to this, that the red one, here some part of the area I have neglected it and here some part of the area we have added it. Okay, this is just the approximation. The tapered bar is approximated like this. Okay, and this average area is considered. Neither I will be taking 60 nor I will be taking 30. The average of this is 60 plus 30 divided by 2, that is 45. 45 will be considered in this. Okay, if you do it a single step, you can take it as 45. That is what I have shown here. Okay, if we take it as a single bar, then we can model it like this. And the average area height will be 45 multiplied by 5 mm, that is thickness, gives you the area. Okay. Now in this problem they had given us to take two elements, where we can take another element. If you see the location of nodes are to be located at the beginning of the geometry and at the end of the geometry. Okay, these two. Another point is, wherever there is point of application of force, you have to place a node. So our three nodes will be 1, 2, 3. This one is for beginning of the geometry, this node will be for the end of the geometry. Here, because point of application of load, we will put a node here. Now in this case we will have one element here and one element here. There will be two elements modeled as required by the problem. Okay, then what will be the area in this case? In this case, if we model it as a two bar, what we'll do is we'll take this as first step here and we'll take another step here. Okay, what is the height at this section? This height at this section is 45. we had just determined, right? Average. Okay, what is the area height at this section? The height at this section is 45. Okay, now what is the area of this section and what is the area of this section? To calculate the area of this section, okay, it is 45 plus 60 divided by 2, and here the area will be 30 plus 45 divided by 2. This will be the height at the two respective sections. Okay, average height we are taking, multiplied by the 5 mm, that is thickness, you will get it area. So this is our model, actual model of having two step. We are assuming it as a two step bar, but actual case is a taper bar. We will be assuming it as a two step bar, one with a height of 52.5 and the other having the 37.5. okay, and if you calculate the area, A1 comes out to be 262.5, that is 52.5 multiplied by area 5 is the thickness, okay, cross sectional area, and area E2 37.5. How 37.5? 45 plus 30 divided by 2, 37.5 into 5 gives me the area 187.5 mm square. Here Young's modulus of the whole section is same, so E1 is equal to E2, that is 200 GPa. okay, and we have located the node, that is second node in between, that is at the point of application of force, that is at 120 mm. okay, so length of the first element becomes 120 and second element is also becomes 120, exactly at the middle we have placed it. okay, so if you just see the final discretized element, it is first node, second node and third node. First element is drawn between 1 and 2, second element is drawn between 2 and 3. okay, by this if we just draw this element connected table, element 1 is between 1 and 2, element 2 is between 2 and 3. okay, these two things. Now what is our third step after drawing this element connected table? It is element stiffness matrix. How to write the element stiffness matrix? You have to use the formula K is equal to AE by LE, 1 minus 1 minus 1 1. okay, by this if you just solve it, A1 is to 262.5 into E1 is 2 into 10 raised to 5 divided by L1 is 120. okay, and 1 minus 1 minus 1 1. Element 1 is between node 1 and 2, so U1 and U2 will be written, that is the displacement associated with it, U1 U2 on top of the columns and on the side of the rows. okay, these are just for the reference. Again, element 2 is A2 E2 by L2, just substitute the value. A2 is 187.5 into 2 into 10 raised to 5, that is E2, and L2 is 120. Solve it, it becomes 3.125. The displacement associated with this element 2 will be U2 and U3. okay, so U2 is the U2 and U3 are written on the top of the columns and on the side of the rows. okay, again for the reference. Next is step 4, that is global vector. Here I have just written the global force vector first. okay, global force vector is F1 F2 F3, that is forces at node 1 2 3. Force at node 1, there is no applied force here at node 1. If you just see, this section is our node 1, there is no applied force here, but there are reactions generated here fixed, because it is a fixed end. Second is this node, okay, where actually the force of 150 kN is applied, and node 3 is again free. okay, node 3 is free. So our global force vector will be F1 is R1, that is reactions at that node. F2 is the force applied 150 kN, and F3 is free, that is 0. okay, just before I go ahead and solve this completely, I will again analyze it, what are the, which side the stresses will be what. okay, as we have done for previous problem, to understand, to check whether our answers will come in that range or not. See here, the force is applied here. it is trying to pull out this section. Okay, it is trying to pull this section, it will pull it. Okay, so the stresses generated here will be tensile. Yes, the stresses generated at this section will be tensile. That is the first element here, and here the stresses will be tensile. Okay, and if you just see this second section, second element, there is one force applied in this direction. The element is here and the force applied is like this. Okay, but see that other end is free. Other end, this end is free. Because this end is free, it continues to move. It just simply moves. It doesn't resist. As it doesn't resist, it doesn't generate any compressive stresses, nor it generates any tensile stresses also. So because of that, if you see, there will be no stresses generated here. In this section, stress will be 0, strain will be 0. Whereas in this section, stress has some value, that is tensile, so will be stress positive will be. Okay, so this is our prediction. Okay, we'll solve the problem and we'll let know what are the results, whether the results will match to our predictions or not. Okay, what we were at the global stiffness matrix. Now how to write the global stiffness matrix? How many number of nodes are there? There are 3 nodes. And what is the degree of freedom for each node? Each node has 1 degree of freedom. So our overall global stiffness matrix has a 3 by 3 matrix, and the displacement associated with are u1, u2, u3. So corresponding columns are to be written, 3 columns, 3 rows are written. Okay, and then referring the element stiffness matrix K1 and K2, substitute the values for u1 row, u1 column, substitute the values for u1 row, u1 column, substitute the value for u1 row, u2 column, u1 row, u3 column. Okay, and so on. Okay, and so on from the above matrix. Okay, fill it, we get this value. As we know that because u1 is not directly connected with u3, the value is 0. Okay, fill those values. 10 raised to 5 is kept common outside here again. Okay, what is your step 5? Write the equilibrium equation. Okay, K into Q is F. What is K? Global stiffness matrix. Q is u1, u2, u3. K is written u1, u2, u3, and global force vector R1 150 into 10 raised to 3 and 0. Next step comes is boundary condition. To check what is the boundary condition, for this problem, again it is fixed at this end, there is free at this end. So our boundary condition will be u1 is 0, that is node 1 is fixed, it is u1 is 0. Because u1 is 0, the corresponding row, this u1 row and u1 column are removed off, and we will end up with this matrix. This 10 raised to 5 remains outside. Okay, after writing this, it is just doing the elimination method, that is we are writing it as augmented matrix. Before that I have just done this 10 raised to 5 taken outside, thrown it on the other side of the equation, and 150 into 10 raised to 3 divided by 10 raised to 5 becomes 1.5 only. Okay, that is the reduced size of matrix, and doing the row operations will make it upper triangular matrix. We will reduce it to upper triangular matrix. After writing it in upper triangular matrix, we will do back substitution and determine u2 and u3. Okay, if you just saw this third row, multiply this row with this column, you have to get this one. From this you will get this value, u3 is 34286.34286 mm. Okay, and similarly if I multiply this first row to this one, I'll get 1.5, that is 7.5 u2 minus 3.125 u3 is equal to 1.5. if you solve this one, you will get the value of 0.34285. okay, now u2 value and u3 value are determined. Just we'll write all the nodal displacement. u1 was 0 because it is fixed, u2 is 0.34285, u3 is 0.34286. What can we see? from this solution, as I had predicted in the middle while analyzing it, what are the stresses generated. Node 2 has displaced by 0.34285. Node 3 has also been displaced by 0.34286. The fourth or fifth decimal is changing, that too by 0.1. It seems that U2 and U3 has the same displacement. U2 and U3 has moved by same amount. Okay, it has just moved. There is no resistance, so I don't think there will be any stresses generated here. Now we will calculate the strain. Okay, that is step 7. Strain is B into Q. B is nothing but 1 by L1 minus 1 1 for U1, that is equal to minus 1 divided by 120, that is length of that element, minus 1 1 and 0 and 0.34285. Okay, so the first element, the strain is 2.857 into 10 minus 3. Okay, calculate the stress. Strain in 2 Young's modulus gives a stress 571.43 is the stresses generated in it. Okay, now calculate the strain in the second element. Strain in the second element is B into Q, 1 divided by L2 minus 1 1 minus 1 1. Okay, and if you are right, the L2 value 1 divided by 120 minus 1 1 0.34285 0.34286. Okay, strain is almost equal to 0 there. If I just simplify this, multiply this row with this column, okay, strain is 0. When you multiply with E into strain, becomes stress also 0. So strain and stress in this element is 0. Now to calculate reactions. Okay, reaction in this bar. Use refer your step 5. In that, calculate the row 1. This is the step 5 equation. In this, multiply this first row with this column, you will get R1. Okay, 4.375 into U1 minus 4.375 U2, 0 U3 gives us R1. Okay, 10:5 is outside. Okay, I just written that. Solve it, you'll get 149.996 kilonewton. Okay, that is what we are telling it regularly. This method gives us approximate solution, not exact solution. Load applied was 150 kilonewton. Approximately the reactions generated here is 149.996 kilonewton. Okay, so determining all this, the problem is over. Okay, next we will solve one more problem, that is problem number 5. I no need to explain how this step bar will be modeled as a two-step bar, but the problem here is different. Okay, before that we'll just read out the problem statement. A bar with a varying cross section is subjected to a load of 400 Newton as shown in the figure. Determine nodal displacement, strain, stress, support reactions in the bar. Consider two element model again. You have to just take two element model. Young's modulus 200 GPa. I have explained the thorough thing of it in the previous problem. What I'll do is I will just model it as two element. How to model it? I'll have to place the node at the beginning of the node geometry. At the geometry, there will be two nodes here. One more node is at the point of application of force. Okay, so overall length is 300 mm. So what 150 is the length the force is applied P. If we go on dividing it into elements, this is the first element. This is the first element which will be generated, and this is the second element. Okay, here the previous section, in the previous statement, there was the height at this was 60 and height at this point was 30. Okay, remember this. There they had given you the height. Here the problem is directly giving you the area at this section is 600, area at this section is 200. If you now do the average at this section, the area will be 600 plus 200 divided by 2, that is 400. At the middle it becomes 400. At this point it is 400. Now what is the average area at this section? If you take, it is 600 plus 400 divided by 2, that is 500 here. And if you take the average area at this point, this is 400 here and 200 here. 400 plus 200 divided by 2 is 300. Okay, that is our okay. Here this part is just to identify what is the midsection area. Then I have taken the average of this section and this section. The area will be at this section, that is for first element. This section plus this section average area gives me the area at this section. Okay, that is the only difference. Now what is the difference in another problem? You can see the problem is having a wall ahead boundary condition here. The element is supposed is to move by only 1.12 mm. If the element moves beyond 0.212, there is a wall ahead and it hits that wall and it is unable to move beyond 0.12. How such a kind of problems are solved? Okay, such kind of problems, what we do? Okay, what are the such kind of examples is you might have seen the railway tracks. Okay, two railway tracks, there is a small gap when you are joining it. Okay, and then because of that elongation there is some gap that you can meet. Beyond that, then the stresses will be generated. Okay, it is similar kind of problem. This kind of problems I think you might have also solved in strength of materials. Okay, I have modeled it as step bar. Okay, see here, this problem will be solved as similar to a simple bar element without considering this. There is a wall ahead here. There is a two-stage problem, this one. First stage is we will be solving this without considering this part, that is the wall ahead. Okay, so u3 is assumed to be free, it totally moves. Okay, and after solving it, if at all the displacement is greater than this 0.12, then we have to implement that boundary condition, else we don't need to implement it. Okay, just check out the steps. We have determined initially the first area of area1 section and area2 section. Okay, area at one section is 500 mm square, area at second section is 300 mm square. Because the element is same, Young's modulus remains same, E1 is equal to E2, 200 GPa. Okay, first step discretization is done. Node 1, 2, 3. Node 1 is between 1 and 2. Sorry, element 1 is between 1 and 2. Element 2 is between node 2 and 3. Okay, that is what is our relation connectivity table. Next come to the element stiffness matrix. Okay, element stiffness matrix K1, E1 E1 by L1, 1 minus 1 minus 1 1. Substitute the values, that is 500 mm into square into 2 into 10 to 5 divided by 150. Just simplify it and substitute it inside, it becomes 6.67, and substitute it all to the auto matrix. And then u1 and u2 are the displacement associated with it. So u1 and u2 are written on the top of the columns and the side of the rows. Okay, similarly solve for k2, a2 e2 by l2, 1 minus 1 minus 1 1. Substitute the value, area is 300 mm square into 2 into 10 is to 5 divided by 150. Simplify it, you will get the value as 4 and multiply it inside the matrix. It is associated with displacement u2 u3 u2 u3 written on top of the columns and side of the rows. Okay, next, global stiffness matrix. How to write the global stiffness matrix? the size of the overall stiffness matrix will be 3 by 3 because 3 is the number of nodes which are present, and number of degrees of freedom for each node is 1. 3 into 1 becomes 3. 3 by 3 is the square matrix for global stiffness matrix. Okay, now refer u1 row, u1 column for each element, u1 row, u2 column, u1 row, u3 column, u2 row, u1 column, u2 from each of these element stiffness matrix. Okay, and substitute the values, simplify it. Okay, you will get this global force vector. Okay, global stiffness matrix. Then for solving global force vector, the force is applied again at node 2, that is of 400 kN. Node 1 is free, but there is a reaction generated, so R1 will be here, and there is a load P here, and there is no force here, so it is free. Okay, so R1 is at node 1, force at node 2 is 400 kN, and force at node 3 is 0 because there is no reaction, no force applied nor reaction generated. Okay, now this is our traditional regular method what we have done till now. Okay, now solve it. Solve this K into Q, that is equilibrium equation in step 5. K is the global stiffness matrix, U is the displacement vector and force vector. Okay, now step 6, this is what I had said you, boundary condition. Node 1 is fixed, so U1 is 0. Also from the figure we can see the node 3 is free, but it can move by only 0.12 mm. Only then how to implement this? How to implement this? But first we will solve the problem without considering this gap, this as a gap, but we assume it as a totally free. After solving, we will check this node 3 displacement. If it is greater than the gap, then we will implement the boundary conditions, or else we just will, if the okay, greater than the gap or not. If it is greater than that, only then the boundary condition will be used, and we will check that what is the reactions induced in that or wall touching. Else, if the displacement is less than that, it is not need to be applied, then no reactions are generated. Okay, first we will solve without considering it as a gap but free end. Okay, so it is u1 is only 0, first row and first column gets eliminated off, we'll end up with 2 by 2 matrix. Okay, 2 by 2 matrix. Now just simplify it. How to simplify it? If you have the calculators, you can directly go with matrix multiplication, and there also you can do it, or else you can also go with this equation method in your calculator. Okay, that is 10.67 u2 minus 4 u3 is 400 into 10 raised to 3. Okay, different techniques you solve it, you will get the value of u2 and u3. u2 and u3 u2 is 0.5997, u3 is also 0.5997. Okay, what has happened in the first section? The stresses are generated, second section is just simply moved. See here, this u3 is greater than what is the gap available, it can only move by 0.12. okay, if it is greater than 0.12, it hits the wall and the reactions are generated. Now what we need to do, we need to say that u3 is 0.12, so u1 is 0, so our new boundary conditions will be u1 is 0, u3 is 0.12. okay, that is our final boundary conditions. Now if you remember the first video which I had released, that is elimination method of applying boundary conditions, I had also insisted there, remember, if the value of the displacement u is 0, then the corresponding row and column gets deleted off. Okay, if the value of that node displacement is known to us, then only the row gets deleted off, because that column is not multiplied with non-zero value, the value exists. Okay, just see here, this is actually this step where you can see u1 is 0, that row, corresponding row and column gets eliminated off. Okay, now because this u3 is 0.12, I have just eliminated this row. I have eliminated this row so that I don't need to solve that row because u3 is known to me. But why I am not eliminating this column is 0 multiplied by 0.12 becomes 0. Okay, minus 4 multiplied with 0.12 is non-zero element. Okay, we cannot remove that. Okay, so this is the reason why we need to retain the column. Now simplify this. What to simplify? Multiply the remaining section, that is second row, you just multiply it. Okay, 10 raised to 5 is kept common. 10.67 into u2 is u2 minus 4 into u3 gives me 400 into 10 raised to 3, that is this side. Okay, simplify it, you will get the value of u2, new value of u2. So our final displacement values are u1 is 0, u2 is 0.4198 and u3 is 0.12. Okay, now so calculate the strains. Strain in the first element is 1 by L1 minus 1 1, and displacement associated with it are u1 and u2. Simplify it, 1 divided by 150 minus 1 1, and displacement u1 is 0, u2 is 0.4198. Simplify it, you will get a strain as 0.002798. Okay, similarly calculate what is the stress in it. Stress is E into strain. Young's modulus is 200 into 10 raised to. I think I have made some mistake here. I think it is 2 into 10 raised to 5. This part I had made a mistake. It is 2 into 10 raised to 5, or it is 200 into 10 raised to 3. Okay, remember it. And now calculate it. The stress 559 is a small mistake here. Okay. Similarly, strain in the second element I have written here correctly. Okay, strain in the second element 1 divided by 150 minus 1 1, and displacement associated u2 is 0.4198 and u2 is 0.12, sorry, u3 is 0.12. Simplify it, you will get a negative strain and negative stress, that is sigma 2 is E into epsilon 2. This negative is because it is compressive now. Okay, it is now compressing that second element. Okay, now calculate the reactions. What are the reactions? Use this step 7 now. Use this step 7. Solve the first row to get R1. Solve the third row, you will get R3. Okay, so if you just simplify here, R1 is minus 280 and R3 you will solve it. It is minus 119. Minus 280 minus 119 becomes minus 399.92. Again the reactions what is generated is equal to the load applied, so our results are correct. Okay, the results are approximate. Okay, now coming to the next part. Next problems are your assignment problems. These 4 problems. Okay, these 4 problems are assignment problems. The only difference I'll be telling it, all the things you need to determine is nodal displacement, strain, stress and reactions. In problem 6 it is similar to what we have solved in problem 1 and 2. The only change is force applied here is in the opposite direction. Okay, so if you take this as node 1, node 2 and node 3, force here will be minus 10 kilonewton. Okay, this is under compressive and this is tensile. Okay, you should get approximate results like that, because minus 10 kilonewton is on the first element. Okay, it is trying to compress it. That is the only change. Okay, Step 7 is what is the similar problem what we have solved in the previous case, that is we have to model it as a two-step bar element and then solve it. Okay, areas they have given, it is 300 and 200. If I just tell you this section, it is 250 mm square, and here it will be 250 plus 300 divided by 2, and here will be 250 plus 200 divided by 2, it is 225. Here it is 275. Here is the average area of these sections. Okay, and then simply solve it. Force is in the positive direction, but the force are applied at both the nodes. Force is applied at node 2 as well as node 3. Reaction is present here, R1. This is the problem which I solved here, but it was tapered word which I had considered while solving. This is the wall head of boundary condition again. Okay, area A1 is equal to A2 here. Okay, this is the first element, this is the second element, because we need to apply load at this point. There will be one more node here. Okay, two element model have to be done. Force is at node 2, node 3 is free. Okay, first solve it without considering u3 as 0.12. just solve by a normal method and check it. If that displacement is greater than 0.12, then you have to solve for u3 is equal to 0.12 and apply that boundary condition and solve it. Okay, and lastly this is problem number 9. Okay, area and Young's modulus at each sections are given to you. First section, second section, third section. Forces are applied at there is no force applied at node 1. Node 1 is free, but reactions are generated here. R1 is there. At node 2 there is a force of 25 kN, that is positive again. Node 3 the force is applied is 10 kN, that is again positive. This is node 4. Node 4 is having a reaction R4, you can take it. Okay, just last hint I'll tell you. In the conventional that is hand solving method of FEM, okay, you can have n number of nodes, n number of elements when if you solve using this computer, with the help of computer. But when you are solving, trying to solve it with the hand manually, okay, if you take 4 node here, okay, this section we are having 4, 1 2 3 4. If it is 4 node, then the size of matrix what we get is 4 by 4. Okay, and if we now apply boundary conditions, this first row and first node and the fourth node becomes eliminated. We next need to actually solve for 2 by 2 matrix at the end. Okay, unnecessarily don't increase the elements. If you go on making 4 by 4 matrix, 5 by 5 matrix, 6 by 6 matrix, 5 by 5 matrix also, if it is at both the ends fixed, then you will be solving for only 3 by 3 matrix. That is okay, you can solve it manually with this elimination method. If you go with 4 by 4 matrix, that is after applying boundary condition, I am telling you. If you go by 4 by 4 matrix, 5 by 5 matrix, then the computation calculation time increases while converting it into upper triangular matrix. Okay, that's the only thing, care has to be taken there. Okay, thank you.